right, ladies and gentlemen. So hopefully we all had great Thanksgiving breaks. Today, what we're going to be doing is we're going to start our unit 4, which is bond energy. So we're going to talk about bonds, breaking them, forming them, and what energy goes into both of these. So if you guys want to open up your iPads and go to Canvas and open up the Introduction to Reactions and Energy worksheet that's on Canvas for today's assignment. We're going to be going through some vocabulary, so some different terms that we're going to be using throughout this unit. And then we're going to talk about endothermic and exothermic reactions just in general and what those actually mean. So the first one says the law of conservation of matter. So for this vocabulary term, we're going to talk about the fact that matter or energy and mass cannot be created or destroyed. Only transferred. So our energy or our mass will never be like just randomly appearing or never randomly disappear. It always has to come from somewhere and go somewhere else. So our matter or energy or mass always have to go from one place to another. It can't just randomly appear and disappear. It has to come from somewhere, it has to go somewhere. That's going to be super important in our reactions. So our reactions are going to be chemical reactions or chemical equations. Where we are changing our components or we're changing our substances from chemically. So we're chemically changing the substances we start with to something new. So we're chemically changing our substances from what we start with to something new. So there's two types of changes that happen in chemistry. So we have our physical changes and our chemical changes. Would you say that me ripping this piece of paper in half, is that a physical change or a chemical change? What is your guess?
Physical.
Physical change. I physically did it. I changed the appearance or the shape or the volume. I didn't change what I have. This is still paper. I can still write on it. I can still use it as a bookmark, whatever I use it for, but it's still paper even though it's ripped in half. Still paper. What about when I take a candle and I light it on fire? What do we think about that?
Chemical.
Chemical change. You're taking it, you're chemically changing it, you're lighting it on fire, it turns into something new. It is no longer that wax that we had before. What about food that you eat?
Physical.
So physically, when you're chewing it, it does physically change because you're just making it smaller. But as soon as it goes throughout your body and you digest it, you're actually turning that food into energy. So it's going to be another chemical change after that physical chewing and swallowing of the food. So it actually does both. We eat it, we make it smaller so we can swallow it, and then once it goes into our digestive system, it actually turns into energy, forms something new, and so that's when it turns into that chemical change. So every time I've asked you, is it forming something new? So when it forms something new, we're going to actually have that chemical equation or reaction. And so we have to be able to write these out. And so when we're writing these out, we have to start with one side and end with a different side. So we are going to start with things called reactants. Reactants. The things we start with. So our reactants are the things we are going to start with in our problem, or our chemicals we're starting with. And then we're going to yield or make. So an arrow, it represents our yield or make. And we're going to make products. And those are the things we're going to make during that reaction. So we start with our reactants, and then we're making those products at the end. Are there any questions so far? All right. So I'm going to talk about this candle some more in terms of systems versus surroundings. So systems are going to be things that we're looking at. So specifically, if I'm looking at this candle, this is my system. My candle will be that system. So systems are just anything that you are specifically looking at, like the zoomed in picture of just one specific thing. So if our system is what we're looking at, what would you think the surroundings are?
The things around the system.
Exactly. Anything that is around the system that is not my system. So if my candle was my system, it's going to be the air, my hand holding onto the candle. Anything else that the candle is not. So everything around that system. All right, so anything that's not the system is our surroundings. These two words are going to be super important when we're talking about endothermic and exothermic reactions. So our endothermic reactions are going to have energy or heat entering the system or being gained by the system. So the system gains or is gaining, oh man, cannot spell. Gaining heat or energy. So our system is gaining heat or is gaining energy. All right. And so then exothermic, what do we think exothermic is?
Losing heat or energy.
Exactly. It's losing heat or energy. All right. So we need to be able to talk about this endo and exothermic reaction in a couple ways. The first way is to talk about it in terms of the system versus the surrounding. So we have to talk about the system and the surrounding of endothermic reactions. If endothermic reaction means it's gaining heat or energy, is the system going to get hotter or is the system going to get colder? The thing we're looking at.
Hotter.
Exactly. So we're gaining energy or heat, or we're absorbing energy or heat. So our system gets hotter because it absorbed or gained heat or energy. So it gets hotter because it gained that heat. So if the system is getting hotter, what do you think happens to the surroundings?
Gets
Gets
colder.
colder.
It gets colder. It has to take that energy from somewhere because remember, our energy or our matter is conserved. So it has to take all that heat from somewhere else. So our surroundings get colder. The heat is being taken away. So heat is being taken away from our surroundings by the system to make that system hotter. So now what do you think happens in an exothermic reaction for our system?
The system gets colder.
The system gets colder, meaning that we lost heat. So what happens to my surroundings? If my system is getting colder,
It gets hotter.
heat is added. So we're adding heat to the surroundings for the system because the system is losing that heat. So it's getting colder, which means it's pushing that heat somewhere else. And then this delta H is just the change in energy or heat. So that delta, that triangle is delta, and it means change in. Any questions on the vocab that we're going to be using? Especially because this vocab is going to come up throughout this unit and throughout the next semester. So you're going to have to know some of these words pretty much for the rest of the semester and probably longer. All right, so let's look at this first example. Let's go through one of these together, and then we're going to talk about the graphs on page 3, and then I'm going to let you guys work. So on page 2, it says we have to identify the system, we have to identify exothermic or endothermic, and then we need to explain why we think that. So this first one, the process is an ice cube melts after being left out on a table. What is our system here?
Ice cube.
The ice cube is the system. It's the object that we're looking at. So if the ice cube is the system, is this an endothermic or exothermic reaction? So let's try to explain what we're thinking and then we'll decide. So the ice cube, is the ice cube gaining energy or is it losing energy?
Losing energy.
All right, I heard both. So somebody explain to me why it would be gaining or losing energy.
Because the ice cube is cold and the table is warm, so it's absorbing the heat from the table.
All right, so the ice cube is absorbing, if I could spell absorbing, heat or energy from the table. So if it's absorbing that heat or energy, did we decide endothermic or exothermic?
Endothermic.
Endothermic is the absorbing. So absorbing is endothermic, which means exothermic would have been releasing, which is the opposite of absorbing. Any questions on that first problem?
No.
All right, so then let's talk about these graphs real quick because you'll have to use these graphs at the very end, but let's decide some information about them. So let's go through actually the first 2 questions on that first graph. This graph right here. Do we think that graph is representing an endothermic reaction or an exothermic reaction?
Endothermic.
All right, I heard endothermic. Why would this graph be an endothermic reaction?
Because the products have more energy than the reactants.
Because the products have more energy than the reactants. Which means energy was absorbed. And then if we're looking at that, specifically looking at the delta H, is that a positive delta H or is it a negative delta H? Is it getting bigger or smaller?
Positive.
It's positive. So our delta H is positive here, which means it's getting larger. It goes up. From reactants to our product, it's getting bigger. So it's a positive delta H. What about our delta H on the second graph? Is delta H over here positive or negative?
Negative.
Delta H is negative here. Is this graph endothermic or exothermic?
Exothermic.
This graph is exothermic. Perfect. And then we should be able to identify why it's exothermic. Are there any questions on any of the work we've done today so far?
No.
All right. If there are no questions, you guys have 8 practice problems with identifying endothermic or exothermic with an explanation. And then you have 3 more problems down here to complete. One is number 2 on our right picture, which is just explaining why you think it's exothermic. The last question on each is just to determine if it's endothermic or exothermic. If it's endothermic, you're going to put that number next to the endothermic side. If it's exothermic, you write that number under the exothermic side. So you're just determining which ones would be graphed based on what you say above. That's all I have for you today, guys. So if you have no questions, you guys are good to go. Have a wonderful rest.